Hello, good evening, all of you. Am I
Good
audible?
evening.
Good evening, good evening.
Yes,
Uh,
we are audible, sir.
yeah, yeah. Sir, Srinivasan sir, just can you please mute yourself? Uh, hello, hello. Srinivasan sir, are you getting me, sir? Yeah. I think my screen is visible to you. My front page, first page. Hello. Any one of you can respond. I think my screen is visible. Hello. Okay, okay, okay. Thank you, thank you. Okay. Today is the week number 5. We will discuss the lecture series, whatever you taught on the week 5. Okay. The subject is hydrogen energy, that is the production, storage, and transportation and safety. Okay. Myself, Subrata Kumar Maiti, PMRF student, PhD students from IIT Roorkee, and course instructor is Professor Pratibha Sharma, ma'am, IIT Bombay. This is thus we will recap the previous things. Basically, today we will discuss the water electrolysis and the current status, global current status, and the Indian status, and we will compare all the electrolysis, all the hydrogen production process. We will compare them and we'll see them. What is the hydrogen production cost for each individual hydrogen productions method? So far, we have studied that steam methane reforming process, autothermal process, and partial oxidation process, and some biological process for hydrogen productions.
ये कितना गोरा है कितना कम
Yes, and lastly, we'll see the all the process for the hydrogen production cost. And basically, what is our main goal? The main goal, globally, main goal is to just reduce the hydrogen cost. Okay, reducing, not only reducing the hydrogen cost, but the hydrogen production should be in a sustainable manner. Okay, thus the water electrolyzer or electrolysis of water or electrolysis is becoming a trending research. Okay, so that thus water electrolyzer reduces the carbon emissions into the atmosphere, thus the sustainable hydrogen energy we can get. Okay, the basic element of water electrolyzer is one separator. This is one separator. This is one separator. It has, you can also say, called that separator or diaphragm, okay, or membrane. Okay, in different method, the different nomenclature is used. Okay, simple water electrolysis cell, it consists of one anode. This is one anode. Anode is basically positive in charge, and another one is the cathode. It is rich of electron, that is the negative charge. Okay, we have to supply power supply, we have to give some power supply. Basically we will use the DC power supply. Okay, and thus the DC power supply, when we will apply through the anode and cathode, what will happen, that the electron will flow through the external circuit. This is the external circuit. Okay, this is the external circuit. You just see, electron will flow through the external circuit, and what will happen in the cell, into the cell or inside the cell. Inside the cell there is electrolyte. The sky blue color is the fill of electrolyte. Electrolyte may be water. You can use water as an electrolyte. You also can use zero point 0.5 molar NaCl. You also can use KOH as a KOH solution as an electrolyte, NaOH as an electrolyte solution as per requirement. Okay, I will ask you, why we'll use NaCl, why we'll use KOH solution, why we'll use NaOH solution as a electrolyte later. Okay, thus one power supply, DC power supply, anode, cathode, and electrolyte, and in between one separator. Also, you can say diaphragm, membrane. Okay, this is used. I have told you that the electron is flowing through the external circuit, but how the ion will flow? Because if the ion will flow, the electron will flow, obviously the circuit should be completed. Okay, the circuit should be completed like this. I have to use one pen, uh, like I will choose. Okay, in this part, the electron will flow. The electron will flow, and this will be electron is coming. This is the electron will coming. Okay, here the reaction will occur. This is the reach of electron. This is the cathode. Okay, in which hydrogen will be evaluated in cathode side or cathode compartment. The reaction will be like this: the H plus electron, it will convert that H, okay, H, and thus two H will combine together and produces the hydrogen gas, and hydrogen will produce at the cathode. And similarly, in opposite at anode side, oxygen will produce. Oxygen will produce. The reaction will be shown in the later slide. But the interesting thing is that I am telling you that the electron is flowing through the upper external circuit. This is the electron flowing circuit through the wire, electrical wire. But how the electron will flow? Obviously, this circuit should be completed. Okay. Thus, the ion should be ion movement should be there in the electrolyte cell itself. Okay. How the ion will attracted? There's H plus ion will attracted to the cathode. Okay, to the cathode. Thus, the H plus will, by combining one electron, the hydrogen will produce. H plus will attracted and OH minus ion will attracted to the anode side. OH minus. Okay, OH minus. Why OH minus is attracted to the anodes? Anode, because anode has a positive charge. OH has a negative charge. Okay, thus OH is attracted to the anode and H plus is attracted to the cathode. Okay, in the electrolyte compartment, in the electrolyte cell, the ion movement you can see, but in the external circuit, the electron movement is there. Okay, thus why the separator? What is the function of this separator? This separator, the function of the separator, there are two functions of this separator. First one is the whatever the gas is producing in the cathode side and whatever the gas is producing, oxygen gas is producing in the anode compartment, you have to separate these two gases. You don't want, it is not acceptable, or it is not acceptable the two gas mixture you will get. Okay, always it is necessary to produce the hydrogen and oxygen separately. Okay, the first functions of the separator is to just separate the two gases to product gas. The second function is not mixturing the anolite and catholite. Okay, as well as ion separations or ion movement, controlling the ion movement. How the controlling of the ion movement we will see in the PEM, proton exchange membrane water electrolyzer, or polymeric membrane water electrolyzer. Okay, we will say there are basically two functions of the separator. Okay, this is a basic principle of the water electrolyzer. I will ask you why we will not use water, but recent technology is using water, but uh, why we will prefer NaCl or NaOH solutions or KOH solutions in this electrolyte cell, water electrolyzer cell or water electrolyte cell. Any one of you can answer me? Okay, I am explaining because I have told you that the ion movement will occur inside the cell. Why the ion movement will occur inside the cell? Due to the potential difference, ion will move to the anode, and another ion is moving, H plus ion is moving to the cathode side. But this ion will move if, let's assume that in a electrical wire, copper wire or aluminum wire. In copper wire, we generally know that copper has a high conductivity. That's why the electrical current will easily flow through the copper. Electrical current will flow better than the aluminum wire because the high conductivity of the copper wire. Similarly, for the ion movement, it should be higher conductivity of the electrolyte solution. If we add NaOH. If we add NaOH, KOH into the water, or if I make the NaOH solution for KOH solution, the conductivity of the electrolyte will be higher, the ion movement will be easy. That's why we will prefer the conducting electrolyte into the cell. But there also has some limitation for using this conducting type solution. But in some electrolyzer, we will use KOH solution. But generally nowadays, modern researchers are going forward or looking forward for the fresh DI water electrolyzer. Okay, this is the basic things of the water electrolyzer. Next is the possible arrangements. This is very simple. Just I will first forward it. This is the gap cell. Like the electrode, two electrode is uh, in a distance. Okay, in between one separator, there is one separator. This is the cathode. This is the anode, and in between one separator and electrolyte also. Okay, this is called the gap cell. We have not, you cannot make this gap so high or so large, because the ohmic resistance will be high. Considering the optimized gap, you have to design the water electrolyzer or gap cell water electrolyzer. Okay, generally the gap, I am working on the electrolyzer. Okay, I am not working on the gap cell electrolyzer, but I did some chloroalkali process. Generally, this gap, the two electrode gap is 2 mm. Okay. Next is the zero gap electrode. This gap you can minimize. Okay. This gap you can minimize. Why you are going for minimizing this gap? I think someone is waiting in the lobby. I don't know why they are coming late. But it hampers some. Okay. Yet I'll try. Okay. Coming to the zero gap cell, this gap is, you can reduce this gap such that, why you are going to reduce this gap? Because the ohmic resistance will be reduced. Because if the ohmic resistance will high, the hydrogen gas production's cost will be high, or cell voltage will be high. You know that the power consumptions of the general power consumption, P equals to VI. Okay, P equals to VI. The main target will be reducing the voltage in the electrolyzer design. Okay, main target will be the reducing the voltage. Okay, how you will reduce the voltage? If we reduce the distance between the anode and cathode, anode and cathode, cathode and anode, the voltage will be reduced, because obviously the ion movement will be easier if the electrode is kept quite in a smaller gap. Okay, this is the concept of the zero gap cell. Next, the uh, latest concept is the electrode pressed against membrane. This is called MEA, membrane electrode assembly. I have also prepared membrane electrode assembly in my research. MEA, membrane electrode assembly. What is membrane electrode assembly? That is the in between. This is very disgusting. Okay, someone is waiting. Just wait. I have repeatedly told you that just you please join in time, because if you don't join in time, it will problem. Okay, because I have some target that I will complete all the things in 2 hours. That's why I am going fast forward. MEA, membrane electrode assembly. This is very important things. That's why I should discuss here. Membrane electrode assembly. This is the concept for the proton exchange membrane water electrolyzer PEM. How you keep the membrane? This is your membrane. Suppose this is your membrane. This is your cation exchange membrane, or any membrane, or maybe anion exchange membrane. The electrode will be pressed. The electrode cloth, okay, or some conducting material titanium felt will be pressed. This cloth consists of electrocatalyst. Okay, the electrocatalyst will be spread over the cloth, carbon cloth, or electrocatalyst, or iridium oxide in the anode side will be spread over on the titanium field, and this is called porous transport layer. Okay, this porous transport layer will be pressed together with the membrane. Okay, and this is dipped into the electrolyte solution, or by arranging one cell compartment. Okay, this is called electrode pressed against membrane. Okay, and now latest technology is like is all of our very emerging technology is the MEA, membrane electrode assembly technology, because here the two electrode gap will be reduced and voltage will be reduced, thus the power consumption P will be reduced, and thus the hydrogen production cost will be reduced. But it is not easy to reduce the hydrogen production cost. Okay, we will discuss later. Okay, and next I will discuss two or three important terms, that is the over voltage. This is the over voltage actually. Over voltage. What is the over voltage? For any reaction, this is the energy state, initial energy state. Okay, the A is reactant and B is the product. B is the product, and when A participates in the reaction, A have to overcome this sort of energy. Okay, this sort of energy. This energy is called over voltage. Here, for the producing of the hydrogen evolution reaction and oxygen evolution reaction, you have to overcome some sort of over potential. We will repeatedly explain, or we will say that the over voltage, over potential. That's why over potential term should be known to all of you. Okay, the over potential term is calculated Arrhenius by using the Arrhenius equations. Okay, for your knowledge, just I am showing this slide, but if you have some more interest, you can go the Arrhenius equations, or you can study the over potential in depth. Okay, like here one man is laying in the bed, sleeping on the bed. That is the A reactant is at its at its initial state. It is not participating in the reaction, but this man have to go to office. Okay, how the change of state is occurring, that after some time he have to stand up and have to sit on the bed, means he is gaining some energy. not gaining some energy, he required some energy. Okay, required some energy, then he will go to the office. The final product will be B, that he will go to the office. Okay, this change of state of energy, this difference, this difference, this difference from the initial state to maximum energy level, this maximum energy level is called the over potential or over energy. This is the basic things, you can go in details. Okay, thermodynamics and cell voltage, you know the reversible voltage is 1.23 volt and thermoneutral voltage is 1.48 volt. Already we have discussed in the earlier lecture. Okay, and what is happening in the reversible conditions, the voltage is 1.23. That is 1.23 volt is required. The minimum water dissociation voltage is required for water splitting is 1.23 at standard conditions. Okay, but in the practical case, what happened? In practical case, there are lots of irreversibilities. Okay, due to the lots of irreversibilities, like in the anode and cathode, there are the over potential. Just I have discussed this over potential. How the over potential will come? Due to the kinetics of the reaction, the over potential will come, and also the ohmic resistance of the cell, that is the in between the anode and cathode. This is the anode and this is the cathode. This is the anode and cathode. Any material have some resistivity. Suppose copper wire, copper has less resistivity, but in every material some there has some resistance. Okay, or if we in cell, anode and cathode, in between the resistance, ohmic resistance means simple, v equals to ir, v equals to ir. This r is the ohmic resistance. Okay, how much voltage is showing, how much voltage difference is in the cell, and current, how much current I am applying in any wire, electrical wire, and you can measure the resistance. Okay, this is the ohmic resistance. This, due to this irreversibilities in the cell or kinetic of the charge, movable charge or ion movement, the thermoneutral voltage or over potential term is coming. Considering all of the factors, this cell voltage, generally working electrolyzer cell voltage is not 1.23 volt, not 1.48 volt. It is beyond 1.48 volt. Like it ranges between 1.8 to 2 volt or 2.5 volt. Okay, 2.05 or above the 2 volt. This is the practical case. Okay, you cannot make the hydrogen production, you cannot produce hydrogen at 1.23 volt. You can produce 1.23 volt hydrogen at 1.23 volt hydrogen, but this is meaningless. Okay, how the irreversibility is coming, I have discussed. The point is here, the internal resistance inside the electrode across the electroactive layer at the interface where the charge transfer occur, means that the ion is receiving charge from the electrode, or electron is receiving, or electron is remove gaining or giving. Okay, in the solution sector, across the diffusion layer, you know that there are two layer. One is the compact layer, another one is the diffusion layer. Due to the diffusion layer, due to this diffusion layer means that the ion is moving, randomly moving. Okay, this randomly moving ion in the electrolyte cell, you have to give some directions of this ion movement. Okay, for giving the directions of this ion movement, you have to use some energy, or the energy will be lost. Okay, this is the irreversibilities of the cell. Okay, this is the very simple slide. Okay, the total cell voltage equals to reversible cell voltage plus reversible cell voltage plus this is the irreversibilities voltage, all the irreversibilities or over potential voltage. How the over potential will come? Due to the ohmic resistance, ohmic voltage, or activation energy. It is coming from the kinetics. Okay, electrode kinetics. And this is the concentration, that is the bulk concentration, that is the for the diffusion layer. This is due to the diffusion layer. Already I have discussed the diffusion layer, how the diffusion layer, where the diffusion layer will create it. Okay, and you know that this activation energy or activation voltage, okay, it is in the logarithmic term. The first zone, activations over potential, one is the logarithmic curve. This is the ohmic zone. Second zone is the ohmic zone. Second zone is the ohmic zone. This ohmic zone, simple vehicles to IR. This is linear variation. That's why it is linear curve. Linear curve means that the xy, this is the x and this is the y. This is the linear curve, and logarithmic curve, you know. Okay, and this is also logarithmic curve, concentrations over potential, not linear. The third zone is the not linear zone. Okay, this you have to remember. Okay, and okay, the at 80 degree centigrade, the the at ideal conditions the voltage is 1.23 volt. Okay, and the at 25 degree centigrade the thermoneutral voltage 1.48 volt. Just to remember these things. Okay, next. Next, kinetic of the electrolysis. This, if you want to study the kinetic of the electrolysis or electrolysis reactions, that is the anode and cathode reaction, is calculated by using the Butler-Volmer reactions. This is the reaction. You can go into details. Okay, the term is already written here. This electrolysis cell stack, you can, there are two different way for arranging the cells, number of cells. Not only you will not use only one cell pair, you have to use number of the cell. That's why the industry wants bulk production or mass production. That's why you have to use cells in a stack. Okay, this is called cell stack, stack. Okay, cell stack configurations. There are two way of arranging these cell stacks. First one is the very simple. You join all the cathode by one electrical wire, and you will join all the anode by one electrical wire. Then the you will apply the DC power source. Here the total I of the stack will be number of the cells multiply individual cells current density or current. Second one is the bipolar or series arrangement. Series arrangement is something different. That is the series. Series means that first cell, this is the negative smaller one, positive larger one. First cell anode, this is larger one is the anode. This is the anode. Smaller one is the cathode. Second cell, this anode is connected to the cathode for the second. Okay, next is the anode is connected to the third cell, cathode, anode. Such a way you will arrange the electrolyzer cell. Okay, this cell arranging is called bipolar or series arrangements. Okay, in series arrangements the total I is same for the all cell. Okay, and voltage is just multiplying, or voltage is the summations of the all cell voltage, or multiply number of the cell multiply individual cell voltage. Okay, this is the best optimize uh, cell arrangements you can go for the design. Next one, this is the very important one formula. We'll you by using this formula we'll calculate the hydrogen production rate. Okay, per hour in terms of normal meter cube per hour. This is very simple. Hydrogen productions rate normal meter cube FH FH2 normal meter cube per hour. Okay, generally it is measured in normal meter cube per hour. Okay, not kg per hour, not cubic centimeter or liter per hour. You can convert it liter per hour. Okay, but general unit is standard unit is normal meter cube per hour. Okay, also you can write in liter per hour, you can convert it. Okay, uh, eta f, this is the efficiency. Okay, this is the efficiency of the cell efficiency, electrolyzer cell efficiency, multiply n is the number of the cell, multiply individual cell current, multiply divided by z. Z is the number of the electron associated with the hydrogen evolution reaction, that is the z equals to 2. F is the Faraday's constant, and this is the factor for converting into normal meter cube per hour. This is the factor. You have to remember this formula for future applications. And where is the n is eta f is the Faraday efficiency. Okay, Faraday efficiency. It is also called current efficiency. Okay, it is also called current efficiency. Generally, this current efficiency lies around 0.95. Okay, you remember this formula. This is very useful formula. Okay, and this is the specific energy consumption formula. This is also very simple formula. Okay, you can go through, and you have already, this is important actually. Okay, this is important. The efficiency of the electrolyzer, this is the cell efficiency. Okay, this is the cell efficiency in terms of gives free energy and in terms of enthalpy. In terms of enthalpy, previously this is called, this is called have you remember this VTP is, what is this VTP? This is thermoneutral voltage or thermodynamics voltage. Okay, and this is the, in terms of G, this is the reversible voltage. Okay, this term will be, I will use, by using this formula will solve one numerical such that it will be more easy for understanding. Okay, summary you can study. Okay, so far we have studied the electrolyzer basic working principle. Now we will see the three different electrolyzer. First one is the most viable uh, technique or electrolysis technique is the alkaline water electrolyzer. This alkaline water electrolyzer is most commercial. It is commercialized technology. Okay, it is most of the industries is install this are using this alkaline water electrolyzer. Okay, this is most easiest manner or easiest way of producing hydrogen, or from the alkaline water electrolyzer the large number of the hydrogen is produces. Okay, in water alkaline water electrolyzer, this is very simple. The some gap is in between the anode and cathode. In between there is one separator. This is the anode and cathode. Okay, and hydrogen is produced at cathode side, and oxygen is produces at the anode side. In alkaline water electrolyzer, as the name suggests, the electrolyte solutions is the alkaline conditions. That means 30 to 40% or 25 to 30%, generally 30 to 40% or 30 to 35%. Okay, more than 30%, 35%. Okay, 35% aqueous solutions of potassium hydroxide KOH solutions is used as a electrolyte. I have already discussed why the KOH solutions is used in the water electrolyzer, because just to increase the ion conductivity of the electrolyte, such that the move ion can move from one place to another place easily. The ion conductivity will be high, the ion movable will be high, ion mobility will be high, the over potential will be reduced. That's why the alkaline water electrolyzer uses the alkaline, means that the aqueous solutions of the potassium hydroxide. In this case, the purity of the hydrogen is little lower, that is the 99.5% or 99%. Okay, as there are the porous separator. Porous separator means some sort of oxygen or hydrogen can mix together. Okay, but when we will use the membrane, non-porous membrane, non-porous membrane means there are no porosity in the membrane. When the membrane will be used as a separator, there the two gases will be separated, strongly separated. No gas mixture will be formed. Okay, that's why uh, this is the some disadvantages of this alkaline water electrolyzer. The thus the modifications is done in latter. Okay, here the anode electrode is used as a nickel or nickel base or nickel foam catalyst. Okay, or cathode is used nickel or nickel based catalyst. Okay, and diaphragm material is generally zirconium oxide or zirfoam. Okay, okay. In alkaline water electrolyzer, the no polymer electrolyte membrane is not used. But nowadays the modifications is going on, the research is going on. They are using the polymer as a separator. In that case, the name will be like anion exchange membrane water electrolyzer. Will coming in the latter part. Okay, this is the cathode reaction, or this is the anode reactions. You can see cathode reaction. Cathode in cathode, hydrogen, sorry, water is reacting with the two electron. Thus, this produces hydrogen and the OH minus ion. This OH minus ion is attracted to the anode side. This OH minus ion is forming oxygen and water and two electron. This two electron is coming in the cathode. This two electron is using. This two electron is coming through the external circuit. This two electron is used in the cathode, and thus the hydrogen is produces at the cathode. Okay, thus the hydrogen is produces at the cathode and oxygen at anode. Alkaline water electrolyzer is a mature technology, reliable and safe life, and less expensive catalyst is used in the alkaline water electrolyzer than the PEM, proton exchange membrane water electrolyzer. Okay, less corrosive than the acidic electrolyte. I mean PEM. Okay, proton exchange membrane water electrolyzer. There is a higher durability. Okay, a slower response to the power fluctuations due to the ion transportation in liquid electrolyte which shows inertia. Because OH minus ion is a heavy ion, it shows some inertia. The ion moment, this is the sluggish OH has a sluggish reaction, or OH minus ion movable. You cannot move OH minus ion easily, but you can move easily H plus ion. Okay, that's why the alkaline water electrolyzer has some slower response to the power fluctuations due to the ion transportations, OH minus ion transportations. Okay, current density and pressure limitations. You cannot go some higher current densities because, and there are some pressure limitations because this is not the membrane electrode assembly system. That's why you cannot receive, or you cannot get some pressurized hydrogen. But if you will use the membrane electrode assembly in the case of the PEM, proton exchange membrane water electrolyzer, you can get pressurized hydrogen in the outlet or in the output. This is the PEM water electrolyzer. Here one proton exchange membrane is used. Here one proton exchange membrane is used. That this membrane may be Neptune membrane. This is the brand name actually. This is chemical name is the perfluorosulfonic acid base polymer or polyether ether ketone polysulfone. These are the polymer you can use to make the proton exchange membrane. This proton exchange membrane only allow the H plus ion from anode to cathode. Only allow H plus ion. Membrane is used for selective barrier. Membrane is a selective barrier. Only H plus ion will move from anode to cathode. In proton exchange membrane, water is fed in the anode side. The water is dissociated and DC power supply is given here, and water is dissociated half O2 and H plus and 2 electron. This 2 electron is moving through the external circuit, and H plus 2 H plus, this H plus is coming to the anode, from the anode to cathode side. In the cathode, H plus, in the cathode this H plus receive 2 electron and this produces hydrogen. This is the basic simple working principle of the proton exchange membrane water electrolyzer. Okay. In cathode, as hydrogen is produced, this is called, the reaction is called hydrogen evolution reaction. Okay, or hydrogen oxidation reaction. Okay, in the anode, the oxygen evolution reaction, oxygen OER reaction. This is called OER reaction. Generally, we will use this term HER reaction, hydrogen evolution reaction. Okay, the catalyst. I am coming to the catalyst part. At the anode catalyst, generally for the PEM water electrolyzer, the catalyst is used iridium oxide IrO2. IrO2. And at the cathode side, platinum powder, PT, platinum powder. Okay. And also at the anode side, at the anode side, titanium field is used. At the cathode side, carbon paper is used for the GDL purpose, gas diffusion layer. Because whatever the gas is produces, the gas is coming through the porous transport layer, and will be go to the atmosphere, or you will receive, or you will store these gases. Okay, that's why porous transport layer is used, and this should be conductive. This transport layer PTL, this is called PTL actually, porous transport layer PTL. This should be electrically conductive. Okay, membrane should be ionically conductive. This should be electronically conductive. Okay, you just remember these things. Okay, all of the things I have already discussed for the PEM water electrolysis. For the membrane, it should be higher current density. Higher current density. The operations should be at higher current density, higher durability, high proton conductivity. High proton conductivity means a large number of the H plus ion will be moving forward, or H plus ion will go easily from the anode to cathode side. The conductivity will be high, proton conductivity will be high, the hydrogen productions will be high. This is why you have to design one membrane. This membrane having the higher H plus conductivity, such that the hydrogen productions will be high, the hydrogen productions cost will be less. Okay. In our lab, we will produce, we synthesize this sort of membrane. Okay. I will show you in the during the end of the classes or lecture classes. I will show some of my research, or what are the how the practically electrolyte cell I will show you. Okay. Advantages. The advantage the proton exchange membrane water electrolyzer has is better choice nowadays for commercialization. Already it is already commercialized. Okay, it is already commercialized, and yet some modifications you have to do for reducing the hydrogen cost. It has some high current density, high efficiency, faster response because here ion H plus ion is moving. Here H plus ion is moving. That means H plus ion is a very smaller ion. It can move easily. That's why it is a very faster response. That's why proton-exchange membrane water electrolyzer has larger advantages than the alkaline water electrolyzer, but the cost of proton-exchange membrane water electrolyzer is very high because the noble material is used, platinum, platinum, platinum iridium oxide. This is a high cost material. They are used for the electrocatalyst. The platinum I bought from Indian mm, company. It cost around 11,000 per gram, 1 gram. Iridium oxide 33,000 per 1 gram. Okay, it is very costly. That's why proton exchange membrane water electrolyzer is good, efficiency is very good, but cost associated cost is very high. Next is the solid oxide electrolyzer. This is under a research study. This is not yet commercialized, but the operation principle you should know. Solid oxide electrolyte is a high temperature electrolyzer. Is a high temperature, high temperature, high temperature electrolyzer. The previous one was proton exchange membrane water electrolyzer, alkaline membrane water electrolyzer. They operate at a temperature range of 50 degree centigrade to 80 degree centigrade, but solid oxide electrolyzer operates at over 700 degree centigrade, over 600 700 degree centigrade. Okay, that's why it is called high temperature water electrolyzer, solid oxide electrolysis. Here the ceramics membrane, not polymeric membrane. Here this is a ceramics material. Ceramics material is used as the separator. At cathode, you will supply water feed, and it will react with the two electron. It will produces hydrogen gas at cathode, and it will produces O2 minus. This O2 minus will attracted to the anode side. This is the anode side. This O2 is coming at the anode side, and this O2 will form the oxygen by releasing two electron. This two electron is connected with the external circuit. Okay, this is the working principle of the solid oxide electrolysis. The advantages of the solid oxide electrolysis, it is not commercialized, but it is advanced technology. It is under development condition. This is high temperature water electrolysis, 700 degree centigrade to 850 degree centigrade. You just remember the temperature range. This has higher efficiency, okay, lower electrical energy requirement. Lower electrical energy requirement means already we are utilizing high amount of the heat or high amount of the temperature. If we use high amount of the temperature, the electrical energy will be obviously reduced, okay, or it is vice versa. Already you have studied. Faster kinetic because at very high temperature the kinetic will be very high. The reaction kinetic obviously, okay. This uses very cheap material, not like a noble material like platinum or iridium, okay. The challenges is degradation challenges because at such a very high temperature the degradations of any material is obvious. Next is the anion exchange membrane water electrolyzer. This is the latest technology. The researcher is this technology is gaining interest among the researcher nowadays. NALCO or some different CSIR lab or some IITs or NITs students are working in this anion exchange membrane water electrolysis. Okay. Here the anion exchange membrane means that the OH some membrane you have to make some membrane polymeric membrane that the OH ion will be selectively pass through no H plus ion. Okay. What happened at anode, coming to the cathode actually, first cathode, in here the water you have to feed at cathode, okay. The water will react with 4 electron, it will produce hydrogen, and this 4 molecule of OH minus ion, this 4 molecule of OH minus ion will attracted to the anode, it will come through the anion exchange membrane. Only OH minus ion will be coming from cathode to anode, and this OH minus ion will at the anode reaction it will produce oxygen and it will produce 4 electron and water also. In anion exchange membrane electrolysis, the anode material, anode electrolyte, anode electrocatalyst, cobalt oxide, CuCO4 for anode electrocatalyst. For the cathode electrocatalyst, for HAR reaction, nickel, cesium oxide, lanthanum oxide, okay, you can deposit it on the carbon paper, okay. This electrocatalyst, you have to remember the name of the electrocatalyst. This electrocatalyst yet lower cost than the proton exchange membrane electrolysis electrocatalyst uses, okay. These things you just theoretical things you can study. The difference already you have studied. I will not go for I will not go into details, but you have to remember that the for the solid oxide electrolysis the electrical efficiency is very high, 74 to 80%, because already at a higher temperature the kinetics is very high, that's why electrical efficiency is very high. But PREM or alkaline water electrolyzer the efficiency is 60 to 70%, it falls in between. Operating pressure is important and temperature is important. Operating pressure is very high for the PEM water electrolyzer, okay, as it uses the membrane water electrolyzer, membrane MEA technology, membrane electrode assembly technology, okay. Why the working pressure is operating pressure is high, the high working pressure is very good for hydrogen production, because if we produce hydrogen as a very high pressure, you have to know uses the external compressor for hydrogen compress. Okay, these are the things. You just go through the table, you can easily understand. Summary you will go through. Okay. Next one is the photo electrochemical water splitting. In photo electrochemical water splitting, the photon from the sunlight will be used for the electrode reactions. Okay. How the photon will, here the photon will produce electron. This electron will participate in the reactions and water will split. This is the main concept. Okay. There are some different layer. First layer is the transparent conductive substance. Next one is the photovoltaic cell. Okay. Photovoltaic cell, it will produce electron. Obviously photovoltaic cell means solar cell. Solar cell produce electron. Okay, electron flow through the electrical wire, that's why current is flowing and fan and light is on. Okay, this is the photovoltaic structure, and in this way the cathode or anode is attached. The in the photo electrochemical cell, the hydrogen is produces, the reactions is like that at anode and cathode. Here the photoelectrodes, the band gap is very important for the photovoltaic cell. Okay, band gap is very important. Just in the photo electrocatalyst, this is the photo anode cell. Photo anode cell. It has some valence band and conductive band. Okay, the electron will flow from the valence band to conductive band, and the this electron will go through the external circuit and it will complete and the reaction will occur and the hydrogen will produce. This is the basic things. Okay, and some titanium TiO2 is very useful material. Okay, semiconductor, not semiconductor. TiO2 is very good material used in the photoelectrochemical cell. Okay, a semiconductor is used in the photovoltaic cell, but here the concept is something different. TiO2 is very good, but here you have to remember the range actually. The for the HER, for the HER case, conduction band. Okay, the electron volt should be minus 4.6 electron volt, above 4 point minus 4.6 electron volt, and in the OER side minus 5.9 electron volt. Okay, that means there are the lots of material, but only the TiO2, this TiO2, only this TiO2 is fall in the range, that is the above, means at the above this range and above this range, valence band and conduction band. Okay, this is a very good material for the photo electrochemical reaction for hydrogen production. These are the theoretical part. I am not going into details. Okay, most of the material not suitable. The band gap. There should be how the band gap is created, because the photon is falling, photon or energy packet is falling on the material, and it is creating some valence band and conduction band. Okay, by creating the movement of the hole and electron and hole pair in the material, thus the band gap is created. Thus the band gap is created, the valency band electron is coming to the conduction band, the electron is flowing, and this electron is used in the electrochemical reaction. Okay, this is the overall working principle of the photochemical synthesis. Just you can go through this slide. Steps involved, major requirement for the photochemical reactions are these are the things. Okay, summary of the photoelectrochemical cell. This water splitting is still at development stage. It is not commercialized state. It has very less efficiency. It is not till now not suitable for the industrial hydrogen production. It is required for the better material. You have to replace the TiO2, or you have to improve this material, or improve the efficiency or stability of the material. Okay, this is the summary. Comparison of the hydrogen and hydrogen production route and parameter. The comparison, okay, SMR reactions, the most suitable technique is the SMR, steam methane reforming technique. The 70 to 80% or more than 80% hydrogen is produced from the steam methane reforming process. Its efficiency is very high, 74 to 85%. Next is the partial oxidation, and some advantages you have to study. Okay, you already know the partial oxidations for hydrogen productions. Okay, the fuel flexibility is very important here. Okay, these questions may come, or this is important. Fuel flexibility, you can use different variety of the fuel for the partial oxidation. Okay, obviously the hydrocarbon. Okay, autothermal reforming. Okay, autothermal reforming, this is the important, that the lower steam requirement than the SMR. Okay, lower steam, this is important, lower steam requirement than the SMR. Okay, autothermal reforming. And SMR, in the SMR, this is the most viable technology, mature technology, widely used method, currently lowest cost for hydrogen production. Okay, uh, large number of the industry running by this technology. Okay, steam methane reforming technology. Next is the coal gasification process. Okay, the efficiency is around 40 to 50%. The syngas is produced at a lower cost, abundant, and cheap feedstock, because coal is cheaper actually, and coal is available. Okay, widely available. That's why here it is written that the feedstock is available. Coal, cheap feedstock is available. Okay, then the methane decomposition pyrolysis. Okay, this is the, you can go through this chart or table. Okay, biomass pyrolysis, also there are the biomass gasifications, dark fermentations, and photo fermentations. Okay, some advantages and disadvantages of this technology. Not these, these are the technology not commercialized, not proven technology, but a little bit of hydrogen you can produce, or it is not used in the industrial scale. Okay, but water splitting at electrolysis, this technology is very important because it produces hydrogen without producing carbon dioxide or carbon footprint. That's why we have to develop this technology, or the production cost of the hydrogen should be matched or brought to the near to the SMR technology, that the hydrogen production cost like 1.5 uh, US dollar per kg of hydrogen. But the at the water electrolysis, the hydrogen production cost is above 5 US dollar per kg of hydrogen. You have to reduce this cost and you have to brought near 2 or 2.5 or 1.5 US dollar per kg of hydrogen production. Why the interest of the electrolysis is important? Because this is mature technology. Okay, no emissions of the renewable, no emissions of the carbon dioxide, while we will use the renewable power sources as a electric or DC power supply, or infrastructure is already available in India as well as outside India. High purity of the hydrogen is, you, you can get the high purity of the hydrogen and oxygen product, but scaling up is a very difficult, because lots of difficulties like some noble material like platinum iridium oxide, high costly material. Okay, capital cost is very high, the membrane cost is very high, Nafion membrane cost is very high, like 30,000 Indian money for 10 centimeter by 10 centimeter Nafion membrane. Okay, this is the, but the we have to produce the hydrogen from the electrolysis only. This is the sustainable, this is the only way for sustainable way for producing hydrogen. This is the summary you can go through. Okay, this is the some important definitions you can go through for a future purpose. Okay, this is also just I am keeping all the things in the lecture, or I will share all the things such that you can study it easily. Okay, in future purpose or in future. Okay, this is important. You have to you should know the scenario of the global hydrogen production. Like up to 2020, 2020, 90 million ton, million metric ton, million ton of hydrogen is produced. Out of 90 million ton of hydrogen, 72 million ton of hydrogen, million ton of hydrogen dedicated for the hydrogen production plant. Dedicated hydrogen production plant means 72 million ton of hydrogen is produces from the this dedicated technology, and 18 million ton of hydrogen is produced from the byproduct technology like chloroalkali process. Okay, that in the chloroalkali process NaCl solutions is used, caustic will produced. The main product is caustic, means that the NaOH, for producing NaOH, caustic soda or caustic, the hydrogen is produces. This hydrogen is produced as a byproduct. Okay, this is the byproduct hydrogen. 18 metric ton of hydrogen, or sorry, million ton of hydrogen is produced from the from the byproduct technology. Okay, and around 60% of the hydrogen is produced from the natural gas only. Okay, 60% hydrogen is produced from the natural gas, 19% from the coal. You have to remember these things. Okay, and byproduct 21%, and low carbon technology like electrolysis technology, photochemical technology, only 0.4% or 0.3% hydrogen is produces from the lower carbon technology or zero carbon footprint technology like water electrolysis technology, photo electrochemical hydrogen productions, reactions. These are the things. These are the projected scenery, the global scenario, like now we are at 20 to 2020 or 2024. Okay, our target is at 2030. The target is for producing 200 million ton of hydrogen, and by the year of the 2050, the target is 500 million ton of hydrogen. And here the plant capacity, now the plant capacity is 0.3 gigawatt. The target is, globally target is 850 gigawatt by 2030 and 3600 gigawatt by 2050. And the carbon capture, you have to increase the carbon capture for reducing or for making the carbon free hydrogen production. Now the carbon capture 130 million ton carbon dioxide is captured by the year 2020. The target 2030 is 680 million ton of carbon dioxide. This is CO2, and 1800 million ton of carbon dioxide will be captured by the year of 2050. This is the target. This is our target. Thus, we can achieve net zero scenario, net zero carbon emission hydrogen productions or sustainable hydrogen productions. This is important. For the electrolysis, 9 kg of water is used for producing 1 kg of hydrogen. H2 is splitting hydrogen and oxygen and hydrogen. You can balance these equations and you will calculate the mole calculate. You will get 90 kg of water, 1 kg of hydrogen. Means that the ratio is 9:1. Okay. For the SMR reactions with carbon capture sequestration, 13 to 18 kg water is required for 1 kg of hydrogen productions. It is very less, still less. But coal gasification, the high amount of the water is required. 40 to 85 kg water is required for 1 kg of hydrogen productions. Why such high amount of the water is required for the hydrogen productions in the coal gasification? Because in the coal gasifications, obviously the coal means carbon will deposited in the catalyst, okay, and carbon will deposited on the catalyst, and catalyst deactivations will occur, and to remove these depositions of the carbon on the catalyst, you have to use large amount of the water. That's why large amount of the water is used in the coal gasifications for hydrogen production. 40 to 85 kg of water required for producing 1 kg of hydrogen. Next is the low carbon. This is also the statistics. You can read it carefully. Okay. This is the cost analysis. I have to I have to mark these things. The cost, the hydrogen cost from the SMR technology, 0.5 to 1.7 US dollar per kg of hydrogen, means the 1.5 US dollar USD per kg of hydrogen, 1 kg of hydrogen, 1 kg of hydrogen. SMR reactions. In the SMR reaction, the hydrogen is produces and costs around 1.5 US dollar per 1 kg of hydrogen. If we if you use the carbon capture sequestration, 0.5 US dollar per kg of hydrogen cost will be extra added. Okay, that means if we use the steam methane reforming with carbon capture sequestration, the total cost of the hydrogen production will be around 2 US dollar per kg of 1 kg of hydrogen. Okay, but using renewable energy, the it cost will be also higher, because the renewable technology like solar energy or wind energy, it is not yet, it is already established technology, but production cost is very high. But yet we will go for the solar energy, rooftop solar energy in our house, because the it has, it is carbon free energy. Okay, this is also some statistics for the China, Canada, Europe. This is important. uh, the solar and wind, the el- elect- electric energy required, or DC power supply required for the water electrolysis, may come from the solar energy or wind energy, because we will not use the energy from thermal power plant. We will use the energy from the solar industry or solar energy. We will use the wind energy, because wind and solar is the sustainable energy, because it has no carbon footprint. That's why the main target is to make the whole system sustainable system, such that hydrogen will produces in a sustainable manner. Okay, this is the hydrogen production cost rate. You can see by this is the target by 2020. This is the 3 US dollar per kg. The target is to reduce this 3 US dollar to 1 US dollar by the year 2050. When we will use the wind, the target will reduce from 4.5 US dollar to 1.5 US dollar per kg of hydrogen production. Productions from these things you will go through. I am keeping all these slides for your future purpose, or future for your future uh, requirement. This is also simple things that you can go through. This cost is just this slide is associated with the cost of different technologies for hydrogen productions, like SMR, partial oxidations, autothermal reforming, coal gasifications, methane decompositions, pyrolysis, biomass gasifications, dark fermentations, photo fermentations. This is the things. These are all the cost. Okay. Next time coming for some MCQ questions. Okay. Hello. First question is, I will discuss 10 questions here. Okay. The first question, just you try to answer the first question. Which of the following is not a component of electrolyzer?
D. Adsorber.
Huh. Simultaneously, you have to think separator membrane, like this is the electrolysis cell. This is water or KOH solution. Okay, in between one is the membrane or separator or diaphragm. Okay, and here is the anode. This is the, suppose this is the anode and this is the cathode, and this is connected with the external circuit. This is anode, so this is cathode. Okay, this is anode positive and this is negative. All the things. Okay, separator is used or membrane is used, electrolyte is also used, electrode, this is electrode, anode and cathode is called electrode. Okay, this is also used, but adsorber is not used. Adsorber, where you have studied this adsorber? Do you remember where you have studied this adsorber?
Hydrogen adsorption.
Pressure swing adsorber, pressure swing PSA. In the PSA unit, there are a different stack of chemicals. There are different stack of chemicals. Will feed the hydrogen gas mixture, nitrogen, water vapor, carbon dioxide, carbon monoxide, nitrogen. All the gases will be absorbed through the by using this chemical, and hydrogen will coming out alone. The hydrogen will coming out in the pressure swing adsorber. Thus, the hydrogen gas you can get the hydrogen purifications of the, this is the purification stage of the hydrogen, this is the adsorber. Okay, so our here questions is not a component of the electrolyzer, so our right answer is the D. Next questions. In an electrolyte cell, the total overvoltage arises due to
All the above.
all the above, but you have to write the equation. So I am writing this equation. What is the total cell voltage? Overall cell voltage. Total overall cell voltage. Total. This is the total overall cell voltage equals to. You say what is the first one is the reversible voltage. A reversible voltage V reversible. V reversible is how much? V reversible is how much?
1.23 volts.
1.23 volt. V reversible plus V irreversible. Irreversible. In the irreversible, under the irreversible, there are different uh, voltage arises. There are different conditions. Due to these different conditions, the voltage losses will occur. That is the under the V irreversible, all of the above. This is the ohmic voltage losses, concentrations losses, activations losses under the V irreversible condition. Okay, is it clear? So our answer is the all of these above. Next, question number 3. Calculate the hydrogen production rate in normal meter cube per hour for N cell. For number of the cell is 40 and current is 28 ampere. Z means that the number of the electron is 2 and the efficiency is 0.95. That is the this efficiency. Which efficiency? Do you remember? This is efficiency is which efficiency? Anyone of you can answer? This is the Faradic efficiency. The Faradic efficiency lies around 0.95. I told you, I discussed already in the previous slide. Okay, it around 0.95. Okay, this is the simple formula you have already studied. The formula is, what is the formula? Formula is F H2 F H2 normal meter cube per hour equals to, what is the formula? The efficiency, Faradic efficiency in F, this is the Faradic efficiency, multiply N cell, this is the N cell, this is the N cell, multiply I cell or current, I cell multiply 22.41, sorry, this is the 22.41 22.41 multiply 36 36 you just calculate 3600 divided by Z multiply Faraday Faraday number multiply 1000, you just calculate. The answer is in the normal meter cube per hour hydrogen. This is the formula. You put, or you know all the value. This is the
Answer is C.
answer is C. Okay. For those, let me discuss that this is the Faraday efficiency lies around 0.95. N cell total number of the cell. This is the current, and this is the uh, constant, or this is a constant just to convert it in Newton meter cube per hour, and Z is the number of the electron participating in the reactions. F is the 96,500. Okay, this is 1000. Okay, so our answer is the 0.4, 0.44. So our 0.44 normal meter cube per hour hydrogen production. Okay, next 4. Question number 4. Which electrolyte is used in the solid oxide electrolysis? Which electrolyte in solid oxide
B. Oh, sir.
huh?
B.
B. Yttria stabilized zirconia means that this is ceramics. Actually, this is ceramics. Yttria is ceramics. Okay, yttria oxide. Okay, this is zirconia or zircon. The company name or brand name is a zircon. Okay, yttria stabilized zirconia. Okay. Do you remember through this zircon or zirconia or yttria stabilized zirconia, which ion is coming through? Do you remember?
Oxygen maybe.
O2 minus. You should remember. This is solid oxide. This is high temperature, low temperature electrolysis.
High temperature.
High temperature reactors. What is the temperature?
700 to 800 range.
Yeah, 700 to 750 to 800 degrees centigrade. Associated all the things you should remember. Here the class we will discuss among us such that all of the students can uh, get some benefits from these classes. Okay, this is the 700 degrees centigrade. All of the things you already know, but this is the discussion classes. Achha, I am asking you one question that iridium oxide. Iridium oxide is a catalyst. Where this iridium oxide catalyst is used? Do you remember? Iridium oxide, IRO2, IRO2. I have told you in the lecture classes. Iridium oxide.
PEM electrolyzer में.
Very good. In PEM electrolyzer, proton exchange membrane water electrolyzer or proton exchange membrane water electrolyzer, the iridium oxide is used as a anode catalyst. Anode catalyst. Anode means positive catalyst. Anode. ANODE. Anode catalyst iridium oxide. And cathode catalyst. Which one is the cathode catalyst? Do you remember? For PEM, because PEM is important, because all the research is going on the PEM, proton exchange membrane water electrolyzer, anion exchange membrane water electrolyzer. I am doing bipolar membrane water electrolyzer. In cathode, Which catalyst is used? This is the questions will may come in your final examination. Cathode catalyst. Which one the cathode catalyst for the PEM? Cathode catalyst is
Platinum.
platinum or platinum powder. Okay, this is the platinum powder. You just remember these things. You have to remember these things, and you have to remember the working principle of this proton exchange membrane water electrolyzer, alkaline water electrolyzer. These are the things. eh. And you have to remember the formulas, and you have to remember some values. Okay, these are things. Coming to the question number 5, which
Nickel
type
based.
which type of the electrocatalyst is used onto cathode in the anion exchange membrane electrolysis? Now,
Nickel based catalyst.
huh, the rare earth metal oxide, transition metal oxide, nickel based catalyst, carbon based catalyst. देखो, for the anion exchange membrane, carbon based catalyst is not used. Transition metal means iron nickel. Okay, it may be used rare earth material. It's also may be used. Nickel based catalyst may be used. Okay, but here the question is in the cathode side. Okay, in the cathode side, in the cathode side, then your answer will be in the cathode side anion exchange membrane. The questions will be answer will be
Nickel based.
no nickel based. Actually, what happened? Nickel based catalyst is used in the both anode and cathode, but nickel and iron will be mixed. Okay, and this is not only the nickel catalyst will be used. Nickel and the mixture, composite material is used. But okay, but for the cathode side, the nickel is also used in the cathode side. Some of the researcher is using the nickel based catalyst. Okay, but here by considering the all the things, if it is nickel iron or nickel copper based catalyst, these sort of things is there, then you can go for the C option, but you have to go to the rare earth metal catalyst, oxide. Okay, actually oxide is used. Okay, so our answer is 5A. Okay, 5A. You just remember this thing. Some of the research, the not only the nickel based catalyst is they have also used. Okay, you also can go for the option C. Okay, question number 6, photocatalysis are used for photocatalysis are used for increasing the band gap, for separations of the charge carrier, for recombinations of the charge carrier, reduce coke deposition. Obviously the coke depositions will not there. Okay, the photocatalysis are used. The obviously the recombinations charge carrier not there, because the charge carrier should be separated.
Increasing
Okay,
the band gap.
for increasing
For
the
separation of charge carriers.
ha
No, increasing.
for separation the charge carrier. The photocatalysis are used for separation the charge carrier. The increasing the band gap photocatalysis photon. Suppose एक material. Suppose this is your material TiO2. Suppose your this is the TiO2 material. This is the photocatalyst material. The photon is coming. Okay. What is happening? already it has some band gap, but due to the already it has some band gap, but you have to separate, sorry, it has no band gap, okay, it has no band gap. You have to, by the using of the the photon, it will create the band gap, and the hole and the electron will flow. The electron will flow from the valence band to the conduction band. uh, so for the separations of the charge carrier, valence band, holes and electron separation, for the separation of the hole and electron, the photocatalysis are used. So our answer B is correct. Next is the basic requirement for semiconductor material in the PC reactions. The band gap equals to photon energy. The band gap greater than the photon energy. The photon energy greater than the band gap. The band gap and the photon energy have no relation. Obviously, the photon photon energy should be higher than the band gap. That's why it will be able to create the band gap. Okay, that's why our answer C is correct. Okay, when the photon energy will be higher than the band gap, then only it can create, it can separate the charge carrier, and it will separate the charge carrier, and the movement will be there, or charge movable will be there. Okay, band gap is fixed. Band gap is fixed for for different material, because you have seen one table. Okay, only TiO2 is lies uh, above the this range. Okay, all other material is falling in between or outside the material. All the material band gap is fixed. Okay, but the separations of the charge carrier, the photocatalysts are used. Okay, for the questions number 6B and 7C is correct. Next, question number 8: which among the following hydrogen productions route can utilize Datier bottom of the barrel feedstock? Already I discussed just few minutes
Steam
before.
methane reforming.
Steam methane
Partial
reform,
oxy Steam methane reforming.
partial oxidation. I have already discussed. Okay, partial steam methane reforming. The what is the feedstock? What is the feedstock used? Obviously, steam and methane is used as a feedstock, and for the combustion feedstock, the combustion feedstock, oxygen and methane is used. Okay, but the Datier feedstock, this is not the Datier feedstock. Datier what? So our partial oxidation. Okay, answer will be partial oxidation. And coal gasification. In the coal gasifications, the coal is used as a feedstock. Autothermal reformation. What is used? CH4 methane is used. Steam methane reforming, methane is used. But partial oxidation, here all of the hydrocarbons, different hydrocarbon may be used. Okay, clear? Question number 9. Question number 9. The amount of the water required for production of hydrogen via coal gasification method. Coal gasification method. Coal gasification method means that the higher amount of the water required. The option 9 kg
40
water,
to 85 kg.
40
40
to
to 85.
85 kg. You have to remember, the for the coal gasification, coal itself produces carbon. This carbon will deposit it on the catalyst. It reduces the catalyst activity, and just to remove or just to reactivate this catalyst, you have to use high amount of the steam. So high amount of the steam means that the 40 to 85 kg of water per kg of hydrogen. Okay, in such a way you have to remember. Next, at present, the cost of the hydrogen production from renewable sources is 0.5 to 1.7 at present from the renewable sources at present. Option 1 A, B, C, D. Which one will be correct? Hello, do you remember? At present, this is 0.5 to 1.7 US dollar per kg of hydrogen. This cost is associated with the steam methane reforming, steam methane reforming without sequestration, without carbon capture, carbon CCUS. This is the steam methane reforming, with carbon capture sequestration, and this is
Please unmute, sir.
this is what whatever this is very high, okay, but this 3 to 8 US dollar per kg of hydrogen is cost from the renewable sources
Sir,
hydrogen production.
voice not audible.
My voice is not coming.
I
Your
think
voice is not coming.
he
Okay.
has left the meeting, so let him join again.
Okay, okay, okay,
Your
just
voice is not coming.
my voice is not coming. Okay, let me check my internet. I think, okay, let me check my internet connections. Let me check. Okay, I have internet. Okay, let me check. Yeah, okay. All are good. Hello. Oh yeah. No, no, no. Yeah, yeah. I'm coming. Thank you. Uh, am I audible now? Am I audible?
Yeah, you are audible.
Yeah,
Now
acha,
audible.
okay,
Right
yeah,
now you are audible.
yeah,
Yes.
yeah. Okay. Mm, and presenting. Yeah. Question number for the question number 10. For the question number 10, at
It
present,
was three
at
to
pre,
eight dollar.
3 to 8. Just let me discuss again. At present, the cost of the hydrogen production from renewable energy sources. Renewable energy sources means that the solar
And
energy,
windmill.
photovoltaic cell or wind energy. Okay, wind energy. Okay, wind and sorry, wind. This is wind energy. The first option 0.5 to 1.7 US dollar per kg of hydrogen production. This cost is associated with the steam methane reforming without carbon capture sequestration. Next 1 to 2.5 US dollar per kg of hydrogen is cost associated with the SMR reaction with carbon capture sequestration. Okay. Next 10 to 15 is very higher. Okay. These options you can eliminate. Okay, final options is the 3 to 8 US dollar per kg of hydrogen production. Okay, uh, this is the end of the MCQ session, but I have also prepared some. Uh, I will discuss some basic things. This was my main target. Just to I will memorize. I will memorize you the basic formulas. This formula is very useful for your understanding. Okay. Sometimes you may get confused. Okay. So one formula you already studied, that the hydrogen productions per hour, that is the FH2. This formula already you studied, that the Faraday efficiency multiply N cell multiply I cell multiply 22.41 divided by Z multiply F multiply 1000. Okay, Newton meter per hour. One thing you have to remember, one formula, one formula, that is the delta H. From this equations, all the things will coming. Okay, delta H equals to, this is the total heat or total energy required for the water electrolysis, equals to delta G. What is delta G? Gibbs free energy. Gibbs free energy is associated with the, any one of you can say.
Electrical energy.
Exactly, this is the associated with the electrical energy. This is the electrical energy, and this is the total energy, and this is the heat energy. Electrical energy. So if you divided by uh, NF, divided by NF, this equation, so it will coming that the delta H divided by NF, Faraday constant, and N equals to 2, this is the delta G divided by NF plus T delta S divided by NF. What is this? Delta H divided by NF. What is this? This is V thermodynamics. This is V thermodynamics. V thermodynamics. THERMO. This is V thermodynamics. Clear? Next one is the delta G by, just I will use the different color. Uh, black. What is this term? This is V. This is V. V reversible. This is V reversible. You just note down this equation, because you will get confused while you will study. Okay. So from these things you have to, step by step, you have to remember all the things. This is V reversible, REV. This is V reversible, and this is the T del S by NF, just left out from term. Okay, this is V reversible. and total cell voltage equals to what? Total cell voltage equals to total cell voltage total cell voltage U equals to V reversible. Total cell voltage equals to 1.23. What is 1.23?
Reversible voltage.
This is reversible voltage. Total cell reversible voltage plus irreversible voltage. Okay, plus irreversible voltage. You know that the irreversible voltage is coming from the concentrations difference, ohmic resistance, ohmic voltage, and the concentrations ohmic and over potential and activation voltage. Okay, these sort of things sometimes confuse you. This is the thermodynamics and thermoneutral voltage. What is thermoneutral voltage? If I ask you the questions, what is thermoneutral voltage? Thermoneutral voltage. Thermoneutral voltage actually, uh, when 1.23 when 1.23 reversible voltage is for minimum water dissociation potential, 1.23 at 85 degree centigrade or 80 degree centigrade, when steam water is at steam. Okay, when water at steam conditions, this voltage is okay 1.23, but in practical, but at 25 degree centigrade means there is no heat added or no heat rejection in the cell. This time the thermoneutral voltage concept is come. This thermoneutral voltage is 1.48. Okay, these the two or three terms: thermoneutral voltage, thermodynamics voltage, or reversible voltage. You have to remember, or you have to write down these equations and write down the things such that you can correlate all the things. Okay, such that you can calculate or you can solve the numerical. Okay, I am putting all the slides for the questions. You can go through or you can directly go through the video lecture. Okay, uh, for the numerical understanding. Okay, this is a simple numerical understanding. If you have any questions, then you can discuss or you can discuss with me. this this sort of problem, all of you get or all of you got this problem, how ma'am has solved these questions. If you have any problem, I will ready to discuss. Okay, okay, this is for today's. Okay, and if you have any questions, or you just mail me, or you can put questions in WhatsApp group, or any way you can communicate with me, or during the classes you can also ask me. Okay,
Can you please give your email ID?
yeah, yeah. My email ID. Yeah, I am giving my email ID. Yeah, I am writing my email ID in the chat box, or I will put my email ID in the WhatsApp group also. I am writing. Just you make one screenshot of my email ID. Subrata underscore Maiti at the rate pe dot iitr dot ac dot in. Subrata, Subrata, my name, and Kumar K underscore Maiti, K for Kumar underscore Maiti Maiti at the rate pe dot iitr dot ac dot in. Okay. Just you make the screenshot or you can copy it. Okay. Thanks for listening me. That's all for today's classes.
Thanks for today.
Yeah. Yeah. Okay. Thank you. Thank you.
Thank you. Thank you.